Okay, now the students will see case 3. Now what is case 3? Just now you see case 3 it is nothing but when damping factor zeta is greater than 1. When damping factor zeta which is greater than 1, what happens? When damping factor zeta greater than 1, where are the poles location? These are the two poles, minus zeta omega n plus or minus omega n into square root of zeta square minus 1. Now see the pole's location. Now where is the pole location? This is the pole's location. Now one pole is minus zeta omega n plus omega n into square root of zeta square minus 1, and another pole is minus zeta omega n minus omega n into square root of zeta square minus 1. This is, let us say, pole P2. This is, let us say, pole P1. But very simple. Now the poles lies on the left hand side of a plane without any second thought. System is stable. But more number of poles on the left hand side of a plane. Now there is a concept called as, this is dominant pole and this one is insignificant pole, right? That is the dominant pole. This is the insignificant pole. Now the students then will start one by one. Now the system is stable, therefore we can find the system time constant. What is the system time constant? Now the system time constant is nothing but negative of reciprocal of real part. What is the real part? This is the real part, minus zeta omega n plus omega n into square root of zeta square minus 1. Negative of reciprocal of real part of the dominant pole, which is equal to 1 by minus, if you take it as a common, zeta omega n minus omega n into square root of zeta square minus 1. Now this is the system time constant. Is there any imaginary part? No imaginary part, completely real part. Therefore the frequency of oscillations are 0 radians per second. Then what should be the impulse response? Now the impulse response in time domain is, now see here, this is the impulse response in time domain c of t, which is equal to k into e power real part. This is the real part, this is the real part. But while more number of poles, we have to concentrate on the dominant pole. What is the dominant pole? If I take minus as a common, zeta omega n minus omega n into square root of zeta square minus 1 into t. Now this is the impulse response, which is the dominant pole response. Now the response which is exponentially decaying. Am I not? Now you just recollect what we are covered previously. Delta 0, it is completely oscillatory in nature. Now you come from complete oscillatory in nature to delta 0 to delta 1. When you come to delta equal to 1, that oscillation nature is completely gone because there is frequency of oscillations omega n. Here frequency of oscillation 0 radians per second, but it just produces a small positive half cycle, that is a damping oscillation. Okay, damping off cycle. But now you come to delta greater than 1, means you just cross the delta equal to 1 value also. 0 is oscillatory nature, 1 is no oscillation but only positive half cycle. But now you cross 1, now you cross 1 plus greater than 1. Now can you see any oscillatory nature behavior here? Can you see any sort of positive half cycle here? Can you see any sort of negative half cycle? No oscillations, nothing. It is completely overcomes the oscillation nature when damping factor delta greater than 1. Therefore, when zeta greater than 1 completely overcomes the oscillation nature, no oscillation nature, nothing. Completely overcomes the oscillation nature. Oscillatory nature is completely eliminated, completely overcome. Am I not? And amplitudes, and finally, ultimately, how the response with respect to time. Amplitudes are increasing or decreasing with respect to time. As time increases, amplitudes are decreasing. Whenever the amplitudes are decreasing, that we called as damping. Whenever the amplitudes are decreasing, that we called as damping. So it will completely overcome the oscillation nature. Therefore, this is called as over damping response. Therefore, when damping factor zeta greater than 1, now this response is called as a over damped response. Overcomes the oscillation nature and amplitudes are decreasing. Therefore, this is called as over damped response. Now, students, note down this. This is the over damped response. Now, can you consider the damping factor delta greater than 1? Can you consider the over damped response? Yes, we consider the over damped response because the over damped response is a stable response. Okay, note down this. Okay. Now, there may be a chance of taking damping factor delta greater than 1 because this is the over damped response. Okay. Now, students will see the next case. Now, that's why the second order system behavior, nature, this completely depends upon the damping factor. When damping factor zeta is changes, the pole location is changes. Therefore, the system behavior is also changes or not? Now, we'll see case 4. What is case 4? Now, these are the poles location previously for a characteristic equation. Now, in this characteristic equation, what I am doing is minus zeta omega n plus or minus omega n into square root of, in under root I can take minus 1 as a common, which is nothing but 1 minus zeta square. Now, this is nothing but minus zeta omega n plus or minus, now this minus 1 is j square. Now, j is coming out of the root, j omega n square root of 1 minus zeta square. Now, see, this is under root is positive. 1 minus zeta square is greater than 0. 1 is greater than zeta square. Therefore, zeta square is less than 1. Zeta is less than 1. Plus or minus 1. Don't take the negative side. Consider always a positive side. Okay. Zeta value is always positive side for a stable system. Now, these are the poles location. These are the poles location when a damping factor zeta is less than 1. Consider always damping factor zeta should be greater than 0. Sir, previous cases why you are not taking a condition of zeta greater than 0 means already the previous cases are zeta greater than 1. Zeta greater than 1 means zeta greater than 0. It is a positive value. Zeta greater than 1 means zeta is positive value, zeta greater than 0. Zeta equal to 1 means it is also a positive value. Therefore, there is no need of put the condition in the previous cases. But here delta is less than 1. It may be negative also. But what I am saying is for a stable system, zeta should be always positive. Okay. For a stable system, here you can write one note also. For a stable systems, damping factor zeta is always positive. That's why there may be a chance of zeta is plus or minus 1. Therefore, don't take negative, only positive side means delta is there. This is the poles location when case 4, which is nothing but damping factor zeta is less than 1 and which is greater than 0. Now, we will see what happens when damping factor zeta which is less than 1 and greater than 0. First you just take the roots of this, then we'll continue the case 4. Okay. Now students, case 4, zeta is less than 1 and greater than 0. These are the poles location. Then where is this poles? Now there is a real part, there is imaginary part. Okay. Now there is a real part and there is a imaginary part. Now first you locate the poles. Once the poles location is available, our answer is very simple. No? Poles are complex conjugate, but there is a negative real part, therefore which lies on left hand side of S plane. When the real part is negative, you blindly go to the left hand side. Therefore this is minus zeta omega n. This is plus j into omega n into square root of zeta square minus 1. This is minus j omega n square root of zeta square, 1 minus zeta square, because this is delta zeta less than 1. Now these are the poles location, but poles lies on the left hand side of S plane. Now without second thought, system is stable. Time constant. Now the time constant, which is nothing but negative of reciprocal of real part. Real part is minus zeta omega n, minus minus cancel, 1 by zeta omega n. Imaginary part will use the frequency of oscillations. The frequency of oscillations are omega n into square root of 1 minus zeta square. Now this is the frequency of oscillations, radians per second. Now the system is stable. Now the response, what is the response? The response is now the impulse response in time domain. The impulse response in time domain C of t, which is equal to some constant into e power real part. What is the real part? Minus zeta omega n into t. Sine or cos. Imaginary part. What is imaginary part? Imaginary part is omega n into square root of 1 minus zeta square. Sine or cos imaginary part into t. Now this is the impulse response. This is the impulse response. The response is exponentially decaying. Multiplied with sine or cos, mirror image. And in the common area, the frequency of oscillations. In the common area, the frequency of oscillations. That's what I'm saying. All these are the previous classes only, but this is for second order we are doing. Now the response is exponentially decaying. The response is exponentially decaying and amplitudes are decreasing. Therefore, this is called as damped frequency of oscillation. The response is exponentially decaying and damped frequency of oscillations. The response is exponentially decaying and damped frequency of oscillations. The response is exponentially decaying and amplitudes are decreasing, so it is called as damping. Exponentially decaying and damped frequency of oscillations. Now, what is the frequency of oscillation? The frequency of oscillations are omega n into square root of 1 minus zeta square radians per second. The response is exponentially decaying and damped frequency of oscillations. Okay, so this is the frequency of oscillations in the damped response. Okay, this is the frequency of oscillations in the damped response. Therefore, this frequency of oscillations is also called as damped frequency of oscillation, where omega d is called as a damped frequency of oscillations. Damped frequency of oscillations. Damped frequency of where omega d is called as a damped frequency of oscillations. Now this is the frequency of oscillations in the damped response. Therefore, this is called as a damped frequency of oscillation. Remember the students, any response is producing exponentially decaying and damped frequency of oscillations is called as underdamped response. Any frequency of oscillations, any response is producing exponentially decaying and damped frequency of oscillations are called as underdamped response. Therefore, this exponential decaying and damped frequency of oscillations are called as underdamped response. This is the underdamped response. And practically we prefer damping factor delta less than 1 because system is stable. Okay, note down this. Okay. Now this is exponentially decaying and a damped frequency of oscillation. Therefore, the frequency of oscillations present in this damped, underdamped responses we call as this frequency of oscillations is called as damped frequency of oscillations. Okay. Exponential decaying and damped free. This is the frequency of oscillations in the damped response. That's why this frequency of oscillation is named as omega d, damped frequency of oscillation. Therefore, I just once again change everything. So e power real part is minus zeta omega n into t, sine or cos imaginary part now I can write it as omega d. And similarly, this is the frequency of oscillation. This omega is represented as omega d. Therefore, this is the real part and this imaginary part is represented as j omega d, and this is the imaginary part minus j omega d, the damped frequency of oscillations. Therefore, now the poles location, which is nothing but, these are the poles location P1, P2, which is nothing but minus zeta omega n plus or minus j into omega d. Therefore, now we can write the characteristic equation as one pole is S plus zeta omega n minus j omega d, and another pole is S plus zeta omega n plus j omega d. So therefore the characteristic equation S square plus 2 zeta omega n into S plus omega n square, which is equal to a plus b into a minus b. S plus zeta omega n whole square, a square minus b square, minus j square means minus 1. Therefore this is omega d square. This is the characteristic equation in the underdamped response. These are the poles location. I just do only omega n into square root of 1 minus delta square is replaced with omega d, where omega d is a damped frequency of oscillation. Again, the same thing with the omega d is the only change. Okay, you just note down this one also. Okay, or where you can remember omega n into square root of 1 minus delta square is the damped frequency of oscillations. Okay, note down this. Okay, now these are the 4 different cases for different damping factors delta. Now, which damping factor zeta is the best one for designing of a second order system? Okay, that also we need to identify. Now, which damping factor zeta is the best for designing of the second order system is also we have to be identified, and the same manner which list is preferable for selecting the best system. Before that, first we'll take one small comparison. Now when damping factor zeta equal to 0, when damping factor zeta equal to 0, poles lies on, when damping factor zeta equal to 0, poles lies on imaginary axis, system is marginally stable. But when damping factor zeta is greater than 0, poles lies on left hand side of S plane, poles lies on left hand side of S plane, and system is stable. When damping factor zeta is greater than 0, poles lies on left hand side of S plane and system is stable. And similarly, when damping factor zeta is less than 0, poles lies on right hand side of right hand side of S plane. Now system is unstable. That is the reason why n number of times I am saying that damping factor delta is plus or minus 1. Then we consider only positive side, because System is stable means only that is lies on left hand side of S-plane. So with this also you can easily understand that the second order system behavior, pole is that side or this side or stable, unstable, marginally stable, it is completely depends upon the damping factor zeta, The second order system, note of the students, this is one note. The second order system complete behavior is depends upon the damping factor zeta. Therefore, all the stable systems should be maintained left hand side. If it is on the left hand side, the damping factor zeta should be greater than 0. That is the reason why in the underdamped response, delta is plus or minus less than plus or minus minus 1, plus or minus 1, but I don't take negative values because already poles lies on the left hand side. System is stable, therefore poles lies on left hand side, the zeta should be greater than 0. It should be greater than 0. Okay. So this is the reason why the second order system behavior is completely depends upon the damping factor zeta, hence proved. Okay. Now I just give the overview of the second order system. Now poles location completely. Now when damping factor zeta is equal to 0, this is the behavior, right? When damping factor zeta equal to 0, system is marginally stable, time constant is infinity, frequency of oscillation is omega n radians per second, and this is called as undamped response. Omega n equals 0 is undamped response. And when damping factor zeta is greater than 1, now this is the pole location, left hand side, which is on the negative real axis, a different location, but I don't concentrate on the second one because this is the dominant pole. Now when damping factor zeta is greater than 1, now this is stable system, time constant is 1 divided by zeta omega n minus omega n into square root of zeta square minus 1. Now all are on the left hand side, therefore no imaginary part, only real part, therefore the frequency of oscillation is 0 radians per second. The frequency of oscillation is 0 radians per second. Now when damping factor delta is less than 1, poles are complex conjugate. When damping factor zeta is less than 1, greater than 0, and this is a stable system, and time constant is 1 by zeta omega n, and damped frequency of oscillations omega t radians per second. Now this is called as underdamped response. This is underdamped response, and this is undamped, and this is named as overdamped. What we are studied, I just give in one S-plane, that's it. Okay, don't confuse. Overdamped response. And finally, damping factor zeta is equal to 1. when damping factor zeta equal to 1, when damping factor zeta is equal to 1, stable because the repeated poles on the left hand side, time constant is 1 by omega n, frequency of oscillations 0 radians per second, and this is a critically damped response. Okay, don't any confusion. Whatever we studied, I just put it on a single S-plane on a one paper itself. That's it. Only that thing I have to be doing here. Okay. So now what we want to be identified, what we can have a look after this. Okay. Then when damping factor zeta, when damping factor zeta is changing from, when damping factor zeta is changing from, when damping factor zeta is changing from 0 to 1, when damping factor zeta is changing from 0 to 1, when damping factor zeta is changing from 0 to 1 means zeta increases or zeta decreases. 0 to 1 means zeta is increases. When damping factor zeta is changing from 0 to 1 means when zeta is increases. When damping factor zeta is changing from 0 to 1, what should be the changes you observe? When damping factor zeta is changing from 0 to 1, now you just see here, now students, just see here, when damping factor zeta is changing from 0 to 1, what should be the changes which we are observed? When zeta is changing from 0 to 1, when zeta is changing from 0 to 1, where is the pole location and where it will move? Okay. When zeta equal to 0, now pole is on imaginary axis, system is marginally stable. When damping factor zeta is equal to 0, pole is on imaginary axis, system is marginally stable. When damping factor zeta equal to 0, what is the system time constant? Infinity. But when damping factor zeta equal to 1, what is the system time constant? Finite. Which means that when damping factor zeta is changing from 0 to 1, when damping factor zeta increases, now the first point you have to be observed is system time constant is decreases, because here it is infinity, here it is finite. Is it decreases or not? Yes, the system time constant is decreases. And the second one is when damping factor zeta equal to 0, now frequency of oscillation is omega n radians per second. But when damping factor delta equal to 1, frequency of oscillation is 0 radians per second. Means omega n and here is 0. Frequency of oscillation is decreases. When damping factor delta is zeta is changing from 0 to 1, now the frequency of oscillations are decreases. Frequency of oscillations are decreases is the second point. Am I not? Here it is completely oscillatory nature. When you come to here, that oscillation nature is gone or not? Yes. And one more thing also, you know that now when damping factor zeta equal to 0, pole is on imaginary axis on the boundary zone. If you go to that side, unstable. If you go to this side, stable. But when delta increases, pole is from imaginary axis to left hand side, and which is nearer to the negative real axis. Means poles are coming to the danger zone or a safe zone. When delta is changing, pole is in the safe zone. Okay. Therefore, when damping factor zeta is changing from 0 to 1 or zeta is increases, now the third point is poles are moving towards the left hand side. Poles are moving towards the left hand side poles are moving towards the left hand side such that the stability is improved. Is it right or not? Next, sir, then is there any other thing? That also you can easily understand. Now we know n number of times we discussed, as pole is moving away from the origin, system time constant is decreases. When pole is moving towards the origin, system time constant is increases. Very simple question. Here time constant is infinity because pole is on imaginary axis. But now see here time constant is finite, and if the pole is moving away from the origin, the system time constant is decreases. Very simple question, very simple answer. See here. Now this is -1. What is the time constant? Time constant is 1 second. This is -2. What is the time constant? Time constant is 1/2, 0.5 seconds. What we can understand, as the poles are moving away from the origin towards the left hand side, system time constant is decreases. Now come to this one. Here is also, here the time constant is infinity. Now here the time constant is finite, decreases, that point which we already noted down. Now my question is, with respect to time constant, which response is having highest time constant? Then if you observe here, this undamped response is having a time constant of infinite. Therefore, what should be the fourth point? This is the first point. This is the first point. Second point. Third point. Now I am asking fourth point. The fourth point is the time constant of undamped. The time constant of undamped, because here time constant is infinity. The time constant of undamped response, which is highest, is infinity, which is greater than next time constant of who is nearer to the origin. That fellow is having highest time constant, but it is already on imaginary axis infinity. Okay. Now who is nearer after this fellow? Who is nearer to the origin? Overdamped response. Therefore, time constant of overdamped response. Time constant of overdamped response. Now, which is greater than? Now, next one is time constant of underdamped response. Next one is time constant of, which is having least time constant. Now, who is far away from the origin or imaginary axis, that fellow is having a least time constant. Am I right? Not. See here, this example you can easily consider. This is 1 second is the time constant. This is 1/2 means 0.5 second. Who is away from the origin, that fellow is having a least time constant, minimum time constant. This fellow is far away from the origin, therefore this fellow is having a least time constant. Therefore, the time constant of critically damped response. Now, this is the undamped response. The time constant of this is undamped response because this is a marginally stable system. We are not use this. This is not supposed to use because marginally stable systems which we are not consider. Now, all these are the stable responses. All these are the stable responses. Among the stable response, which response is having highest time constant? The overdamped response is having highest time constant. This is the highest time constant. Now the time constant is very high. What happened? The settling time is completely depends upon the system time constant. When time constant is more, settling time is more, it will take more time to settle, no? Which means that when the time constant is highest, response is slower. Slower are also called as sluggish. Sluggish means slow. Now, when time constant is less, settling time is also less, no? Very less settling time, which means it will take very less time to reach the final value. So, the response is faster. So, slower, more time, highest time constant. When time constant is more, the response will take more time. The response will take more time to reach final value. When the time constant is less, the response will take very less time. N number of objective questions, students, from here, n number of objective questions. Now, what happened when damping factor zeta is changing from 0 to 1? Okay, now this is one important question. When damping factor zeta is changing from 0 to 1, what should be the changes taking place in the second order system? When damping factor zeta is changing from 0 to 1, now first one is time constant is decreases because poles are moving towards the left hand side, and poles are moving towards the imaginary axis to the left hand side, frequency of oscillations are decreases. Poles are moving towards the left hand side, therefore system stability is improved. And pole is away from the origin, time constant is less. Nearer to the origin, time constant is more. This is the order of the time constant. So, over damped is highest time constant, therefore slow. Now, it will take more time. Now, critically damped response is faster. Now, time constant is very less. The time constant is very less, therefore, it is faster and it will take very less time. So, time constant is highest is over damped response, highest time constant is over damped response, least time constant is the critically damped response. Clear or not? This is very important question. Now, n number of bits from here. When delta is increases, what happens? When delta is decreases, then you take a reverse of that. Now, delta is changing from 0 to 1 means delta is increases, but delta is changing from 1 to 0 means what? When delta is changing from 1 to 0 means delta is decreases. When delta decreases, all are reversed. When delta decreases, time constant is increases. When delta decreases, frequency of oscillation is increases. When delta decreases, poles are moving towards the danger zone, towards the imaginary axis, such that system stability is decreases, and time constant is increases. When time constant is increases means then poles are moving towards the imaginary axis. Okay, that should be the reverse thing. Reverse analysis you can easily do it once if you understand the forward analysis. Okay, now just take a copy of this.